Hi, welcome back to AP Physics C, Unit 2, Newton's Laws of Motion. So this is the final video for this unit. So this is going to focus on centripetal force, something that we can ultimately revisit when we do rotations here in a couple units. Okay, so an object undergoing circular motion must be accelerating because it's changing the direction of its velocity. So when we do centripetal force, when we talk about centripetal or circular motion, what we're really looking at is uniform circular motion, right? So UCM at this point in time. Then we'll get into other force, other circular motion by changing the tangential acceleration. But centripetal is going to keep the object moving at a constant speed, but consistently or constantly changing the direction, which does cause an acceleration. And this acceleration we know as centripetal acceleration, or A sub c. And it can be calculated in two ways. The first way is just the simple way of v squared over r. So the speed of the object squared divided by the radius. Or in a more rotational method is omega squared r, which omega is the angular speed. If you've taken AP Physics 1, this was something talked about in Unit 7. Okay. Now, because we have an acceleration, any net force that is causing UCM is called centripetal force. All right, so it's going to be F sub c, right, is equal to m times AC, or you can plug in what AC is to get other versions of this equation. So you can see how how it's affected. Right? The centripetal acceleration and the radius have an inverse relationship. So if I decrease the radius, my centripetal acceleration will go up. If I increase my radius, my centripetal acceleration will go down. But AC and V are directly proportional to each other, which means if I increase my V, my acceleration will go up. Okay? And you see the force is affected the same way, right? If I decrease my R, my force will go up, right? If I'm doing mv squared over r, and if my speed goes up, then my force goes up. All right. Now, one thing to note is that centripetal acceleration and centripetal force always point to the center of the circle, right? So if I'm spinning something around, okay, the word centripetal means center seeking. Okay, so FC and AC will always point into the circle. Okay, the V is what we really call a tangential velocity, which sits out on the object, right? And so this is why things will want to go in a straight line when taking a turn, because that's the way the speed wants to go, right? Some of the most common questions, aside from just spinning objects over your head, are cars taking a turn. And so if I'm doing a free body diagram of the first car here, right, I'm going to have, and this is on a flat surface, I'm going to have my two traditional ones, Fn and Fg, and then I'm going to have probably friction running around in here. But something to note is that the centripetal force is not a force drawn on the free body diagram. It is the result of all the forces that are acting, right? And so my FC would be hanging out up here, right? Because I know that FC is a net force. It is not a force like friction or normal force or weight, but it is a net force. If I look at my NASCAR on the bank turn, right? Think about the bank turn as a, as an inclined plane, okay? And the difference really is that with our bank turn question, typically with an inclined plane, we're going to change the axes. We're actually going to not change the axes because our centripetal force is always kind of, is into the center no matter where the way the circle is situated. Okay. And it's always kind of, you say, parallel to level ground. All right. So that does change up a little bit of the way that we do our calculations, because Now the only force that would be in one dimension would be our weight, which then means we have to break up Fn and Fx, or Fn to Fnx and Fny, and then you have to break up your friction to Fx and Fy. But we're going to do the banked turn as an example here in a second. But just remember that centripetal force is not one of your forces drawn on the circle or on your free body diagram. It is the result of the forces acting on the circle. All right, so oftentimes where we see this is, NASCAR. So there's a lot of banking on these tracks. But the cool thing is, like, they do it in such a way that they don't slide up and down, right? So the way we look at curves on some test tracks and race courses such as Daytona International Speedway in Florida are very steeply banked. This banking, with the aid of tire friction and very stable car configurations, allows the curves to be taken at very high speeds. To illustrate, calculate the speed at which a 100-meter radius curve banked at 31 degrees should be driven if the road were frictionless. Okay, so if I take my car, right, I would have normal force and weight. So we're assuming frictionless, right? So we don't have to draw F on there at all, but we do have to account for now that Fn is the vector that is broken up into x and y components. Okay, so this would be Fny, this would be Fnx. Okay, and so this will also, because this is the banking, the angle of the banking, that it flip-flops our sine and cosine, much like when we do the weight, on an incline plane, it flip-flops it. So Fnx will be Fn sine theta, Fny will be Fn cosine theta. And the way I like to think about this, instead of making it x and y, it's really like circular and non-circular, right? So circular, non-circular. And so the forces that are in the non-circular will be Fny, right, minus Fg, and we're not accelerating in that way, okay? So we would say Fny equals Fg. Again, notice that in the problem, they don't give us mass because something interesting will happen. So it ends up being Fn cosine theta equals mg. And so Fn would be equal to mg cosine theta, right? That's going to be important because in the x direction, or the circular direction, we will have an Fn running around in there. So we would have Fnx equals mv squared over r, right? Or really it's equal to MAC, right? But AC we're calling v squared over r because we're looking for the speed. So this would be Fn sine theta equals mv squared over r. But Fn over here we found to be mg over cosine theta. So mg over cosine theta times sine theta equals mv squared over r. Here's that interesting fact again. M goes away. And so I do some solving, multiply both sides by r. Sine over cosine is tangent, so I'm going to get Rg tan theta equals v squared, which is good, right? That's where we want to be. And now we just take the square root, and now we can plug in numbers. So square root of 100 times 9.8 tan 31, and we would go 24.4 meters per second, right? And if we want to do like a miles per hour rate, so 24, right, meters per second. 1,600 meters is 1 mile, again, rounding that. 3,600 seconds is 1 hour. So I'm going to do 24.4 times 3,600 divided by 1,600. And so basically the minimum speed that they could take this at, hold on. Okay. So that would be 54.9 miles per hour, right? So if they go below that, then the friction would come into play. But if they go above that, they're fine. Okay. All right. So that is the end of this unit, right? So there is some calculus involved, right? Especially when we did drag force, and understand that you could find acceleration by taking the derivative of velocity.